can blur the rest of you. Fantastic. Okay, so for the moment I see some of you, but that's fine. So welcome to the course. Finally, we can start. And the first day, the first lecture, this is the first full lecture. And as I mentioned in the end of the last welcome introduction meeting, the first lecture is about maps, one-dimensional maps. And this is a very powerful tool to study a lot of phenomena, especially outside of physics, like population dynamics. And these tools are really important also for the theoretical part of our course, because it will be a nice introduction and a hallmark of chaotic phenomena. So once you really understand and grasp these simple one-dimensional maps that we will talk today, then all the rest of the course, at least the phenomenology behind the things that I will talk about in the course, it will be much clearer. So try to keep up with the lecture and ask questions and interrupt me if you have any doubts whatsoever, because this is extremely important to understand really well. So if it were a normal lecture, I would have entered the room and brought a statement, a question on top of the room. And you would have entered already and maybe chatted a little bit, maybe about the question. That really rarely happens, but it's always my hope that it does. So I can share my screen right now, advanced sharing. So share screen, and I will share the screen of my iPad. Okay, so bear with me a second. Fantastic. Okay, so this is the question that I have on my screen. That is a substitute for the blackboard. How can we describe population dynamics? And I don't, just a second that I'm trying to pin my video. There we have it, fantastic. Okay, so the question is, how do we describe population dynamics? So we have a population and we observe the population every year and we make a census and we kind of establish what is the population at any given year. And then we want to describe how this population evolves in time, year by year, in a discrete fashion. And of course, the population of any given year, oops, let's write it in white. So is it fine, the white blackboard, or you prefer a white whiteboard?
I think white would be good.
White would be good. Where can I set it up? I thought I had it and now I don't. So in the setting,
I think I saw it when we were scrolling the upper bar. It said
saw it?
color.
Ah, view, maybe it's here, view. There it is, okay. So better this way, more clear? Okay. So the question is, how can we describe population dynamics that varies year by year? So the first thing that we can imagine doing is describe the population of any given year in function of the population at the year before. So we say that the state of the system, okay, so the state of the system X at any given year I is simply a function of the state of the system at the previous year. Or we can say X of I and I plus 1. Let me check in the notes what convention do I use. Yeah, plus 1 and I. So we say that the state of the system at the year +1 will be a function of the state of the system at the present year. So in this case, trying to describe the population, we will describe the population of the next year in function of the population of this year. So it's this very simple formalism. I think there is nothing simple you can imagine. It's discrete, and basically everyone can try to model this. Even people that count your taxes are managed to do this. So you don't need the physicists to talk about maps. But even with this extremely simple structure, mathematical structure, we can describe very complex and rich phenomena that we will see in this lecture. So this is called first return map. First return map. So this is the first return map, and it's first because it's the function of the state at a given time depends on the function of the state at the previous step. But you can imagine doing the same thing where the function of the state 2 steps after will depend on the function of the state of 1 step up before, okay? And in this case, it will be second return map. So let's just write it here just for fun. So this would be a second return map. Okay, and then you can imagine a third and so on and so forth. And these higher order return maps have some use in the study of the systems or in their description. So let's assume that these, the population grows each year with a given factor. So the most simple thing you can imagine to model the population of a system is saying that the population at the year +1 is equal to some factor, some reproduction factor in function of the population at the present year. Okay, so if we imagine that a population of rabbits, each year they make 5 children, and then this factor R here is 5. And then each year they make 5 children, so a couple of rabbits will make 10 children in 1 year, and then you will have 10 rabbits, or actually 12, and then it will multiply and will grow a lot in very few years. So this description is basically a linear description. And why we call it linear? So linear means that so the function of alpha x plus beta y is equal to alpha, the function of x, plus beta, the function of y. Okay. So this description is it linear? So that's the question that I usually ask. And how will it proceed year by year? So what will we expect that the population evolving in this way will behave, how it will behave? And since we are in this time and age, I think the answer to this question should be obvious to you. So does anybody want to intervene? Silence?
It should be an exponential growth.
Exactly. So the solution for this map, it would be a simple exponential growth. So and at the given j time step will be r to the j times n of 0. So this will be an exponential growth or decay, because if r is greater than 1, you have exponential growth. But also we should not forget that if r is less than 1, then you have exponential decay. So that's a very intuitive way of representing certain behaviors that in this historical period are very important. So everybody knows right now that we have to be very careful with exponential and with this factor r especially, because it will take very, very few steps to have a huge increase in the population. So the exponential model then, it's quite a consequence of a growth which proceeds year by year with a certain coefficient. So that's the, or step by step with a certain coefficient. That's the origin of the exponential growth. And the point is that the modeling power of exponential growth is fairly limited, because any population will exhaust the resources of the environment that it lives in by increasing exponentially. So it will take a definitely not very large amount of steps to exhaust all the resources. So the exponential growth can be representative of the population. That could be the population of a certain species of animal in an ecosystem, the population of humans on Earth, or the population of a virus in a population of the affected by a virus in a given population. But this growth cannot go on forever, because pretty soon, due to the properties of the exponential, it will saturate all the ecosystem, all the available space that this exponential can grow in. So if we imagine that there is a certain ecosystem that limits the growth to a certain n max, then we can rewrite this relation in a very easy way by considering a state x of j that is simply the n of j, the number of any thing that I want to model, of n number of animals, the number of people affected by a virus, the number of humans in a given environment, divided by the maximum number that this can have. This is again a very simple and easy model, and we can say that if we want to model a system that where f of x that is greater than 1, that means f of n max of n is greater than n max, then some catastrophe will happen, and this will result that the next step there will be nobody left. So this is a very very simple to model such a system, or at least to model the step where it reaches like this. So if I admit that that is the case, and I make a simple map that is structured like this, and then I have, this constraint of the ecosystem, then it would be pretty pretty boring in a sense, because the system, the population will grow exponentially until ecological catastrophe. This is basically the definition of ecological catastrophe. This is not a model that needs to be taken lightly, because ecological catastrophe happen. They happen with population of animals on an island if the ecosystem is small enough and animals don't have any predator but just have food, then they can exhaust the food at their disposal and completely starve in a matter of weeks, while the population took years to reach a certain number. So this happened on an island on the coast of Canada or Alaska, now I don't remember, with a population of elks or moose. And this happened to the inhabitants of Easter Island, basically. They cut down trees, and they cut so many that not a single tree remained. And this was the end of the poor folk that lived at Easter Island. So this happened, but it's not very interesting mathematically. So the next thing, the next approximation that we can have is constructing a function that has, maybe this is too small, is it? Can you read the equations well? Is everything all right with the setup as it is?
I think so.
Okay. So if I don't hear you complain, I assume that everything is going fine. I see that there are some chat messages. It looks good, exponential. Okay, fantastic. I will keep the chat on so I can see everything. Okay, so I was saying, so the exponential that I modeled before. So let's write it like this. So the exponential or the linear map were resulting in a map that looks like this. One way to comfortably describe maps is by plotting the state of xj plus 1 in function of the state at xj. Since this is a function, this is, because I established it at the beginning, it is a function, has some nice property. The most important property for us is that it's deterministic. So given a state xj, it will for sure happen that the system will evolve in the state xj plus 1. There is no noise, and there is no splitting. It's not that the system can evolve either in one way or another way. It can only evolve in one way. This is because of the properties of inactivity of functions. So a way that is really convenient is to plot. Basically, this is the plot of f of xj that is equal, that I establish is equal to rx. So j. So that's a way that is convenient to plot. And then we know that when we have such an exponential, what happens is exponential growth. Okay. And in the case that I establish this n max, the only thing that changes is that I have a discontinuities. When x is equal to 1 or greater, this goes to 0. So the next step would be all that. And this will reflect in a graph over time. So this is the steps j, and this is x at each of the step j, that will grow exponentially up to a given moment where I will reach or surpass the value n max. So let's pick up the blue. I'm a fan of colors, so I will use it a lot. So this is n max. So when I will reach this value n max or surpass it, by the next j, it would be only catastrophe, 0. And then since the population is 0, they cannot multiply anymore. I will say 0 forever. So I hope this is super clear. If it's not, please stop me. Feel free to stop me. But what's the next thing I can imagine? So the next degree of approximation, if you will, of the evolution of a population. So the function f that I want to model, and now we'll use blue. Yeah, why not? So this is still x of j plus 1, and this is still x of j. Okay. And then the function that I want to model right now will have 0, 0. It will map 0 in 0. So what does it mean? It means that there is nobody in the population. If everybody's dead or nobody is ever born, nobody can born. So the next year, for a 0 population, the next year the population will still be 0 and will continue to be 0. Okay. And then, so this is for 0. Another thing that they want is that for 1, this is also 0, to representing that there is a maximum number. And when I reach this maximum number of population that the ecosystem can support, then an ecological catastrophe will happen and will completely destroy the population of the next year. This can be exactly by exhausting the ecosystem resources, or by the fact that in the case of a virus, if the virus, if everybody in a population catches the virus cannot be transmitted to anybody else. And therefore, the next season, the virus will completely die off. In this very simple model, of course, this is not the whole story, but this is a simple model that is quite effective to model a lot of things, and it's theoretically extremely interesting. So the first thing that I can imagine happening will be something that starts exponentially and reaches 1 exponentially, and then it connects these two smoothly. So it will be something to connect smoothly. It will be something like this. So my drawing skills leaves much to be desired, both on the whiteboard and on the iPad. But I think you can understand it. Okay. So the important feature of this, it would be that here the maximum corresponds to 1/2. Okay.
I have a question about
Yes.
the graph.
Yes.
So this graph is the x-axis is the current population and the y-axis is the next population.
Exactly. Yeah.
And it assumes that the current population is disappeared at the next generation. So they only count for the new population generated from the current population.
Yeah, exactly.
Okay.
So that's one way of seeing it in this case. So it's extremely easy to understand it in this way. So if I have a given number of children, then only the children will survive. Of course, you can map one to the other because it's very easy to kind of renormalize this growth factor R in the case that the whole population dies, or in the case that the parents survive. Of course, it will not be possible to model a dynamical population that will survive and die off with certain probabilities, and on average, the parents will survive for a given number of years and will reproduce for another given number of years. This is more complicated than this simple model can represent. So you can think either that the parents live forever, and then you simply say that the growth factor is given by the number of children plus parents. So for example, in the case of rabbits, if the growth population, I assume that R is equal 10, it means that if the system is 2 or r is equal 5, sorry, if the system is 2 at step at the beginning, at time step 0, at time step 1, the population will be 2 times 5. That means 10. And this can be given either by the two parent rabbits making 5 children and then dying off, or 5 children each, so 10 children and then dying off, or by assuming that they make 4 children each and then survive. So you can see it in both ways and does not change. The only thing that you cannot model with such a simple model is assuming that the parents live for a certain number of years that is completely different from the steps, and maybe they have statistical distribution of the number of parents that live, and maybe they are reproductive, they are reproducing only for a given subset of years. So is it clear? Did I answer?
Yes, it is clear.
Mm-hmm. Other questions? Okay, then I will go on a little bit. So I was saying, given this assumption that I have an ecosystem, that I have to and I have to consider the fact that the ecosystem can support a maximum number of population, then I have to assume that, it's not that I have to, but the easiest thing that I can imagine to model this ecosystem is to imagine that there is a maximum population, so the population can be represented as a fraction between 0 and the maximum, and when it reaches the maximum, the next generation will be 0. So the function f of xj, in this case, will still be 0 for 1. And then I want to model it in a smooth way, so that there are no discontinuities and nothing strange happens, such as in this case, that rabbits multiply like rabbits without caring for the environment until the environment collapses. But in this way, smoothly, I can model a more sophisticated dynamics where the population reproduce within the environment, and if there is less food or less people to infect for a virus, then there will be less chance of a virus infecting a new generation. Or if there is less food, there will be less children the next year, because some rabbits will die off of hunger and some rabbits will multiply less. So this is a more smooth way of representing these ecosystem dynamics. And there is a very simple function that can represent this growth, that is something like this. Oh my God, I'm very sorry. I don't know how to fix my iPad in order not to do that. The only thing that I can do is fix my writing. Okay, so f of xj that is equal, I remind you, to the state of the next year or the next time step will be given by rxj. So this is exponential, but time 1 minus xj. Let me check. Yes, I use the same notation in my notes and in the book, I think. So that's a fairly simple function that respects everything that I wanted to have in my model. So in this extremely simple function, what happens is that when xj is equal to 1, then this term is equal to 0. When xj is equal to 0, then this term is equal to 0. So in both cases, this will go to 0. In the proximity of 0, 1, this will grow linearly. And in the middle will bend smoothly. So this should be clear that this function so can I move this? Let's try to do this. I want to do something very sophisticated. Okay. Wow. Okay, this is much better than a whiteboard. Okay, so if I assume something like this, what happens the next year? So this is even in a such simple model with such simple function, this arises very complicated behavior that we will see in the next hour or so. So this is called logistic function, logistic function. And the behavior that you will have will depend very much on R. So in the next hour, we will see that for a small r, this will go, well, if the r is really, really small, so if the r is less than 1, then this will decrease exponentially. So this is for r greater than 1, sorry. Then 1. Exactly like the exponential in the case that r is greater than 1, I have exponential growth, but in the case that r is lesser than 1, I will have something like this, exponential decay. And the same will happen here. However, if r is greater than 1, use opposite color. Well, I will adjust it later. So if r is greater than 1, what happens in this case, if r is slightly greater than 1, then what happens is that it will grow exponentially at the beginning, because for small population, this will grow exponentially, exactly like before. But then when the population reaches the maximum population, it will kind of saturate and reach a plateau. So you will have something like this. For r greater than 1, but r less than 2. And then for some magic number that is 2, r will start to oscillate between 2 and 3. And we will see next hour why. And the last thing that I want to say, and I don't know which color to pick. Let's pick this dark yellow. I hope you can see that. For r greater than 3, this for the green, the important thing to notice is that it will oscillate, but will reach a, let's see if I can, okay. So it will grow exactly like before, exponentially. And then it will oscillate, but will reach the same plateau, or well, not the same plateau, but some plateau. So we grow more, oscillate, and then reach some plateau for r between 2 and 3. For r greater than 3, however, it will continue to oscillate. Now the graph is getting pretty crowded, but I hope you can follow. This is for r between 3 and some magic number that we will see after. And if it will oscillate between 2 numbers, and if r increases again, it will oscillate between 3 numbers, and if r increases again, will oscillate, between 2, between 4, or between 8, and so on and so forth. Will oscillate between more and more states until it will arrive to a point where the movement of the population will be basically will move around all over the place and will not have a periodic behavior and will move apparently randomly. But this will not be random, actually. Will still be deterministic because it's still determined by this logistic function. The problem is that it will be extremely difficult to predict what happens if you don't have exactly numbers. And this is the regime that we call chaotic. And then something even more funny will happen, because If you increase again after the chaotic regime, then you will have a moment in which the system will oscillate between 3 values now. And then it will be chaotic again. And then it will, the more you increase this R, the more you have regimes with definite periodic oscillations and chaos. But it will be more and more towards chaos. And this is exactly what the course is about. And this extremely complicated behavior, I have it. It's difficult to understand, to grasp why such a simple equation gives such a complicated and interesting dynamics. But one thing that I want you to notice immediately is that if I have x of 1, this is simply be given by the logistic function of x of 0. Okay? If I have x of 2, this of course be given by the logistic function of x of 1. But in function of x of 0, this will be a more complicated function because instead of x of 1, you have to substitute the equation that you have above. So this will be r square x of 0. Well, no, let's write it in this way. Let's try to keep one page. So this is r square x of 0, 1 minus x of 0 time 1 minus r x of 0, 1 minus x of 0. So you see that iteration by iteration, this will get more and more complex behavior. This is r cubed, x of 0, 1 minus x of 0, and then you will have to substitute x of 0 each time here it repeats x of 0. You have to substitute the logistic function each time here above it repeats x of 0. So this will be again the same that you have above for x of 2. So this is r square x of 0, 1 minus x of 0 times 1 minus r x of 0, 1 minus x of 0. And x4 will be extremely complicated. So you see that iteration by iteration, the description gets more and more complicated and will be more and more rich. And this is the kind of the origin why you have such a complicated behavior in such a simple function. So I think now we can take a break. Oscar has a question before the break. Was the video unclear? What did you find unclear? Exactly, yeah, Veritasium has a nice video, yes. This last part was a bit unclear. What do you need to understand right now? So what was unclear, Oscar? Can you tell me? The behavioral solution? No, of course you cannot imagine why this is so complicated right now. You can only, with this qualitative description, you can only grasp that there is more than meets the eye. And this behavior, it's, I tell you how it is. And now, in the next hours, we will see how to derive that you have this complicated behavior for this simple map. Okay? Good. Do you have any other question before the break? If not, we can take a 10 minutes break. And so I stop the sharing. I pause because this is something that can interest to your students, to your colleagues. So your question was about the fact that when you model mechanical systems, then you have observed that the simulation becomes unreliable after some time. And then you asked if this is also the case here. So your question has kind of two sides for what I can say. So on one hand, we have the fact that you have simulations of mechanical systems, and this is also an interesting thing that relates exactly to the topic of this course. We will see by the end of the course the simulation of mechanical system, both dissipative and conservative systems. And we will see how chaos kind of arises naturally, and it's very common in conservative systems. So if you have an Hamiltonian and then you want a solution of a many-body Hamiltonian, then it's very often chaotic. Or if you have an Hamiltonian with non-linear components, so if it's not an harmonic oscillator or a very common system, then it's very easy to make arise chaotical behavior. So this is also something common in all chaotic systems, the fact that the simulation is not reliable after a while. And I didn't introduce that much because I talk about the introduction in the introduction meeting, but this is kind of a feature that is common in chaotic systems. And this is not an exception. So also in this case, you have that the behavior evolves in a way that is really much dependent on initial condition. And this is also the case. So when the regime starts to be chaotic, the regime that you start with, you will have that the final state of the system will oscillate between values really with a fine dependence on your starting condition. If in this specific case, if the R is very small, then you will have this exponential decay, or you will have this sigmoid function. And this is also called the logistic function that is very famous for right now, for the modeling of the virus and the current epidemic. So in this case, the system is not chaotic, and therefore the simulation is quite reliable in the sense that the system that you try to model behaves kind of like that way. It moves towards a fixed value. And if you change a little bit, it doesn't change much your final results. Your asymptotic tendency will be given by the R factor, will not be given by your starting population. However, if you go into the chaotic system, then what happens is that your system will oscillate, the population will oscillate year by year quite wildly, and this behavior will really depend on your initial condition. You will have that for a population that changes by 1 or 2 units, you will have completely different results. So we will see that that in the case of population dynamics, you will have that in some cases, population with 1 more animals at the starting condition or 1 less will make the difference between this population going extinct or more or less oscillating in a rigorous fashion. So this is kind of what makes the simulation unreliable in a sense, because when you are simulating, you don't always have a complete information. In fact, you never have it in the case of mechanical system, because you have to put your springs in a given specific position. So you will not have an infinite amount of digits representing the position of your spring. And this will introduce some uncertainty in your simulation, and this uncertainty will propagate into later in time. So while the simulation is very reliable at the beginning, because it does not depend at the very beginning at the finer details of the starting condition, the more you progress, the more the system will evolve in 2 completely different ways if you put one situation or the other. In fact, I think I can show you the graph that is in the book of how chaos was discovered. It is very much similar to what you described. So let's see if I can find the picture. This is easier with when I have it on my hand. So I will share the screen. Oh, it's up. So it's up. Okay, there it is. So this kind of old style without colors. Let me share the screen. Share screen. this. Okay, so now you should see the screen, and this is page 10 of the book. And there are two simulations drawn on top of the other. This is the arrow of time, and for the starting point of the simulation is very, very close. So actually, I can even take the Lorentz figure where chaos was discovered. Why did I took the example at the beginning of the book? Let's see if I can find it. I will find it now. So the very first case where this phenomenon was observed, and this phenomenon is known as sensitivity on initial condition, SIC. So this was the very first graph of the phenomenon that you are describing. And it's something that can be noted only when you have reliable physics simulation. So once you can kind of track computationally the progress of your of the solution, in this case of coupled differential equations, then you can observe this kind of behavior that you could not have imagined before finding a numerical solution. And in fact, this was the graph that first discovered the sensitivity to initial condition. This graph was discovered by Lorentz, and in the description of the course, I put a documentary where they filmed Lorentz in his own office, and you can see how very, very, very old-timey computers were made. And in this case, you have these very interesting phenomena of sensitivity of initial condition, because Lorentz kind of let the system evolve for a while and then noted down the number corresponding to a certain state of the system, to a certain time. He says, okay, the state of the system has these properties, and wrote down, since he wrote it on paper, it was having only a certain number of digits. And he wrote as much as possible, maybe 6 or 7 digits, but say, okay, that's enough. It doesn't change that much. 3 digits is written here. So he wrote the 3 digits, and that's fine. And he says, fantastic, this is my starting point. And he went on for a coffee break or whatever, and then he came back and compared the simulation that was running before and the simulation that he started again with these time steps. And the results was that for a while they follow pretty closely, but after a while the solution is completely different. So if you can see, I don't know how to annotate on this Zoom thingy. Let's see if I can, yeah, it doesn't matter, annotate, yeah. So if you arrive here, no, I cannot annotate.
Sorry, the shared screen is not working.
Oh, really? Sorry. Your screen sharing is paused. Why the screen resume share? Ah, it was interrupted. Okay, I'm very sorry. Okay, so annotate, it doesn't work. Yes, it works now. Okay, so if you look here, then the state of the system goes into a completely different direction. And we will see this. And for a while, follow closely, and then it goes completely into a different direction. So this is the sensitivity on initial condition. A very, very small difference in the initial condition determines that the system evolves into a different way. And this is a very common feature in chaotic systems. So this is one thing that you can observe in simulation regarding mechanics in plenty of different situations. So let's stop the thing so you can look at me again. So you can observe in all chaotic system, and it's an hallmark of chaos. So it's one of the way that you say, okay, this system is chaotic or not. And okay, so I hope I answered your question, because I went on for 10 minutes, but it was very important. So this is something that you observe in plenty of different systems. In the case of Lorentz, it was a model of weather, and the same can be observed today. This is why weather reports are reliable today up to 3 or 4 days, maybe. In the past was a little bit less because the computer power was less, and the statistical analysis method were not as advanced as today. So it's slowly moving towards, but this really impossible to make a prediction that is reliable in 50 days or 100 days. And it's exponentially more difficult to make one more day of reliable weather prediction. What you can do is climate prediction, which is another thing, and it's an average value. And that's also one of the takeaway message of this course, that despite the fact that you have chaotic behavior, and this chaotic behavior determines that you cannot predict the exact state of the system in a long time in the future, but you can see behavior, general behavior that happen. And you can see trends. How does the weather evolve season to season? That's extremely easy. Everybody did that since the beginning of time, noticing seasons. But you can be more specific and notice the fluctuations between seasons, year by year, and make long-term prediction, which are not weather prediction, but are climate prediction, which is a different thing. And okay, so I hope that now the context is a little bit more clear regarding the course and why are we doing this. And this is exactly the logistic function is extremely important because it's very important in these days because it gives rise to the logistic function. The logistic map gives rise to the logistic function, which is very much used to model epidemics. And it also gives rise to chaotic behavior. And the way we can see it is not through mathematical analysis. We can see some features in such a simple system like the logistic function, and in the next hours we will see that. But the way that you really understand the system, what is chaos, why is it, at which condition does it arises, and so on and so forth, is also through numerical simulation, because that's the only way that you can really put forward and study systems. How do they evolve in a systematic way and for a long time steps? Because, for example, the thing that I did, now I will share my iPad once again, the thing that I did just before going to break, showing you how complicated it grows to be the logistic map step by step. So it grows more and more complicated, as you can see here. So you can imagine what happens by step 10. So you can do it by hand. It's just simple arithmetic. It's something that you learn in middle school, but it becomes longer and longer. And at a certain point, it becomes so long that does not make any sense to you anymore whatsoever. So you have to rely on numerical calculations, or at least computational calculation, if not numerical. So I hope that's good. Do you have other questions regarding the first half of the course of the lecture? No? Okay. Let me check and pull up the chat. Fantastic. Okay. So if you don't have questions on the first half, we can proceed. And we can proceed on how to study these maps. So we've seen that you can, the maps are deterministic. Given one initial state can evolve only in one way, progresses very systematically, one step after the other, and can evolve only in one way. So it's completely deterministic, but it gets so complicated that it looks like random, but it's not. It's a different behavior. Now, it would be nice to, despite the fact that you have to rely on computers when approaching this type of systems, mechanics, it would be nice to gain some insight before going to numerical calculations. And analytical, you cannot calculate X for a given step, J for a general step J in function of the initial condition, because that would be completely unpractical. This grows and it's out of the question to do it analytically and by hand. But you will have, in some cases, the fact that the map does not oscillate or move chaotically, but reaches a fixed value and there it stays. So in this case, you have that xj plus 1 that is equal to f of xj is equal to xj. When this happens, you have a fixed point. Because it means that the system will, if you reach a point, xj, where the next iteration will be still be xj, then it means that the system will evolve up to there and will be fixed there onwards. So these fixed points, I usually denote them with an asterisk. So these are fixed points. Is it? I hope it's clear, because I mean, you arrive to a certain point which is fixed, and then it stays. So then the j plus 1 will be the same, and the j plus 2 will be equal to the j plus 1, which is equal to xj. So it will be again the same. The j plus 3 plus 4 and so on will be like that forever. So this is basically the definition of the fixed point. And this you can calculate also for the fixed map. And you can find it for the logistic map. And the fixed point of the logistic map, to find them analytically, it's not immediate, but it's very easy to find them graphically. So I have that if I represent, as I often do, my map, considering xj plus 1 xj, and then the logistic map, it's like this. This is 0, this is 1. Then I have a super nice feature that is a nice way to represent this fixed point, which is the, I don't know how to say it in English, is the line that divides the quadrant into equal parts. And this line is the line f of x j is equal to xj. So it's the line that crosses 0 and has slope 1. So this is a very special thing, because each of the points, the length on this line will be a fixed point, because the definition of this line. Then the logistic map grows like this. So the crossing between this line and the logistic map will be the fixed point. So this is x star j. Okay? Is it clear? But also here is an x star j, of course. Right? Because if I start in 0, I will stay in 0. Okay. So if it's not clear, please stop, because this is very important and we'll get a little bit more complicated soon enough. So let's zoom in on this. Oh, I can do this instead of redrawing things. Okay, if we zoom in this case, I cannot zoom in more than this, but I think this should be enough. How do I calculate the trajectory of my population? Let's do another map before this. So let's draw it a little bit larger. And let's do a case which is slightly simpler before that case. So I still have, yeah, let's draw it a little bit less slopey. Okay, like this, perfect. I'm becoming decent, maybe. Okay. So this is your line, and this is your fixed point. Okay, so this is the same. It's only a logistic map with a different R that then meets this bisection secant of the quadrant in a different point. Okay, and if I zoom in, I cannot zoom in too much, but I hope this will be enough for my purpose. I can kind of track the evolution of the population on this logistic map and on this graph. So what happens is that I start on xj that has a given value, okay? So this can be x0 or can be even xj prime, whatever. So I arrive to have xj at the given value. Xj plus 1 will be simply be obtained by doing this. Now, since this logistic map in this portion of this of the map is above the line f of xj is equal to xj. So since it's above this line, it means that xj plus 1 will be larger than xj prime, okay? And if xj prime plus 1 will be larger, it will be somewhere here. I don't rewrite the prime because it's I don't have the space. So xj plus 2 in this case. And then this is larger again, and this is larger, but it will be closer and closer one to the other and approaching closer and closer the fixed point, okay? Is it clear? So if you approach it one by one step by one step, it would come closer and closer and approach this fixed point as an asymptotic behavior, in other words. This can be also seen, this is equivalent, you can represent it in this way. Tac, 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 and so on and so on. And we reach closer and closer to the fixed point with this kind of staircase between the xj equal to the line here of f of xj equal to xj and the logistic map. This is because xj plus 1 will be, so xj plus 1, what is the value on the x is exactly xj plus 1 here is here, okay? Is it clear? That arrives here. And then bounces up and then arrives here. Because let's do it like this. So when you arrive to this specific point, f so f of xj plus 1 is equal to xj plus 1. So the coordinate on the x-axis is equal to the one on the y-axis. So because of the definition of this line. So when you arrive here, basically you can just consider that this is the projection of xj plus 1 on the x-axis and also on the y-axis. And therefore, the next step will simply be given by the projection of this xj plus 1 that meets the logistic map and then continues on this trajectory. Okay, is it clear? This you can see it on the book in this way. Let's see, I hope it will not stop my iPad sharing. Let's see. So this is by watching the book. It's represented in the proper section. The thing that I just explained in this way. So I hope you see the screen, okay? So this is just represented like this. And I hope it's clear. You go from a given xj, when you meet the logistic map, this defines your xj plus 1. When you're on the y-axis, when the y-axis meets again the line y equal to x. This defines your new xj plus 1 on the x-axis, and then again, when it meets this new xj plus 1, it meets the logistic map, it defines xj plus 2, and so on and so forth. And you continue and you continue. And you can see on the line, you see that the steps get smaller and smaller, and on the graph that I draw, you get the steps get smaller and smaller, and closer to this fixed point. Okay. So I hope this is, let's see if it's seamless to do that. No, I still have to push the screen mirroring. It's not a big deal, but I have to do it. Okay. So on the other hand, if you are in this situation, what happens is that it's exactly the other way around. So let's see if I can zoom it and draw it in a decent way. This is more difficult to draw, but hopefully I will manage. So if you start by given xj, the xj plus 1 will be given up here and then here. So this will define the xj plus 1. Okay. As you can see, you are not reaching monotonically this position, the fixed point, but you are oscillating around it because you started below the fixed point with an x that is smaller than the fixed point, xj star, but then the next iteration, it's above. And it's not only above, but okay, in my crappy figure, you cannot see it very well, but usually what happens is not only that is above, but that is unstable, that it grows the distance step by step. Okay, so this is xj plus 1, it's here, that corresponds here. xj plus 2 corresponds here. xj plus 3 corresponds here. xj plus 4 corresponds here, and so on and so forth. I hope the screen is synchronized with my voice and you don't have a delay, so that you can kind of get the intuition of what I'm saying. And this is also in the same page of the book. It's shown with a more refined drawing, but I think these drawings help you when you draw them together when I speak. Okay, so is it clear? A little bit. Do you have questions right now for me? So are you still alive? Did you sleep? Fall asleep? It was too boring, too slow, too fast?
No, it was good.
Okay. Okay, you sweet, I mean.
Andrea?
Yes. Oof, careful with your microphone. Yes? Yeah, tell me.
Yeah, my bad.
Yeah, now it's fine.
Yeah, we got several connections here. In the upward slope, then you approach the fixed point.
Yeah, in this case.
Yeah, and you get steps in smaller increments until you arrive at the fixed point. But then in downward slope, you get like an oscillating, well, something that oscillates and gets bigger and bigger.
So the point is this about the slope or that is upward or downward, or is it about the magnitude of the slope? Because here, if you draw the derivative of this, I don't know what color to write, but let's write orange. So if you do the derivative, even if my drawing is crappy, you can see that the derivative grows like this. While the derivative was quite flat.
Yeah.
And nice, okay? So, and you notice that on my drawing, almost it could be stable. So if you do the same drawing, I will not do it because I don't have that much time. If you want, I can do it to you later. But if you do exactly the same drawing with a downward slope, but it is very gentle, you will oscillate around, but you will still reach the fixed point. And you will asymptotically reach the fixed point. Just not in a monotonic asymptotic like usual, but kind of a damped oscillation around the asymptote. Okay. While if the slope is very big, then what happens is that you are getting away from the fixed point. So in this case, what we are talking about is stable or unstable fixed point. Okay. And this depends on the slope, on the derivative of the map at the fixed point.
Does anything special happen for large positive slopes?
For lower positive slope.
Large positive.
Large positive slope. Exactly the same happens. If you have a large positive slope, you get away from the slope. So it will not happen on the logistic map. That's the thing. You cannot see it on the logistic map, but you can imagine that you have a map that is like this. Okay, sorry, my crappy drawing. So it has to be that is a little bit like this. I don't know, something. No, my drawing is too bad. So, but you have to imagine that your map is not monotonic, then it can happen that your slope is high on the when you meet the fixed point, and then the same principle applies. So when you are around of the fixed point and the slope is high, what happens is that here you are at a slow pace and you are moving away from the fixed point, you see? And if you are above, again, what happens is that you move away from the fixed point. And in this case, you reach this other fixed point. But okay. Do you see it?
Yeah.
Yes. So as you see, depends on the slope. And the reason why it depends on the derivative of the slope is that it all depends if the next step is going to be larger or smaller. If the difference between one step and the next and the fixed point will be larger or smaller than 1. So basically, what you have is that you can demonstrate it in this way. So I think I have just the time to do this. So if you have a difference, so this is, what's the name of this? McLaurin? I don't remember. You are fresher, you should tell me. So basically, you have this expansion that you can approximate the difference between 2 points as the derivatives times the difference in x, okay? And this can be the derivative in one or the other point or in the middle. There are some numerical recipes. Analytically, it doesn't matter. Analytically, you can pick either one point or the other. And since this is an approximation, then you will have a square terms that will be of higher order. But when you calculate it numerically, you can find, if you use the middle point, it's better. Exactly when you calculate the derivative numerically, if you use the middle point, works better than if you use the standard analytical formula, because analytically it doesn't matter, but numerically it does. So therefore, if you do this, and you want to calculate the difference between a given xj and the fixed point, this will be given by Yeah, no, let's calculate before the difference between the fixed point and your starting point. So I did it with the, like this. Okay, so this is given by f prime. Since I can choose, I choose the fixed point, the derivative at the fixed point, because this is extremely convenient for my purpose. Sorry. So this is, I skipped a bit. So this is like this. So this can be represented as x1, but okay. So the difference between the two functions. So basically, if it's getting closer like this or not, depends on this expansion. And these, the arguments of the function, the argument of f of x star is x star, and the solution of x of x star by the definition of the fixed point is still x star. And then this is x star minus x0, okay? Therefore, after a certain number of steps, minus fxj. So this is given by f prime of x star I forgot the absolute value because this works not as an absolute value, but I'm only interested if it's going closer or away. And this is given by the absolute value of the derivative x star minus minus xj minus 1, if you want to do it like this. But this, it's also equivalent to x star of j. So after a certain number of steps, I will be exponentially approaching the fixed point, or I will be exponentially getting away from the fixed point, depending on my on the derivative at the fixed point. Therefore, if what matters is the absolute value of the derivative at the fixed point. So if the absolute value of the derivative of the fixed point is lesser than 1, what means is that after a given number of steps, after j steps, I will be a number lesser than 1 to the power of j, so a very small number times the average, the absolute value of the distance between the starting point and the fixed point. So I will be way, way closer to the fixed point. So this is very stable. This is an attractor. Or stable. On the other hand, if f prime at the fixed point is greater than 1, what happens is that after a certain number of j, I will be 1 point something to the power j, so I will be very much away from the point that I started for. So this is an unstable point. And I have other two special cases that applies. If it's like this, is undecided. If it's equal than 1, then what you have to do to discover if you're approaching the fixed point or getting away from the fixed point is expand on the higher order of your Maclaurin expansion. And then what else? Yeah, if f prime x star is equal to 0, then if your fixed point not only is a fixed point, but the derivative of the fixed point is 0, so it's a maximum or a minimum of your map, what does it mean? That this is super stable. Because what happens is that in only one step, your point, whenever it starts on your map, will reach the fixed point, or will reach very, very quickly the fixed point. In first approximation, in only one step will reach the fixed point. Okay? Good. What else? We talked about the sign. This is also important, because as you noticed here before, there is a difference if the sign of the derivative is positive or negative, if the slope is going upwards or downwards. And the difference is that if f prime of x star is, let's consider, greater than 0, then the approach or the repulsion will be monotonic. Okay? And on the other hand, if f prime of x star is lesser, sorry, I wrote 1, but I said 0, and what I meant is 0. So if the derivative is lesser than 0, then what it means is that we'll alternate up and down, or in other words, oscillate. Okay, because as we've seen before, if the slope is downwards, you have this oscillation that the value that your function is going to have is greater, and one step greater, one step smaller than the fixed point. So we'll go back and forth in this way. Okay. So what else? We have 7 minutes, and I'm almost done, because I can explain you what I said at the beginning. So let's go through it one more time, well, one step, and then I will be open for questions. So in the case of the logistic map, I assume that you are very familiar with derivative, and it's a very easy function. So you are all familiar with it. So in the case of the logistic map, what happens is that f of x star will be given by x star. So in the fixed point, it will behave like a fixed point, like the definition of the fixed point that I gave you before. And this, in the case of the logistic map, simply is the logistic map. And this means that x star is equal to what? Either 0, as we've seen before, or to another point. If it's different than 0, then what I can do is to divide by x star, and I will get 1 equal to r. So you can make your very easy high school calculation that this is given by this number, where this is r. Okay? Do you understand my small r? I think I had problems another year. Let's write uppercase. Okay, very good. So the fixed point is this. Now what I have to do is to calculate the derivative at these fixed points. Let's do it. Okay, the derivative at these fixed points will be simply given by when it's 0, the derivative, the first order derivative, will be simply r for x star equal to 0. And when it's this, then it would be 2 minus r. And this, again, you can do it. I will come back to it next lecture, but I want to flash it to you so that for the other fixed points. For x star equal to 1 minus 1 over r. Okay. And basically, that's it. This is the explanation on the behavior that I observed, that I told you before. Because for r less than 1, what happens is that you don't have a fixed point between 0 and 1. So it means that x star, this other fixed point, this will not be between, yeah, I don't want to write it, it's boring. So the only fixed point is 0, there it is. Then, and then what does it mean is that 0 is a fixed point because f prime in 0 is r, that is lesser than 1, and that means, I would like to have some pointer. Well, I will discover it later, but so in 0, f prime is equal to r, and that means that if r is lesser than 1, then this is a stable fixed point. However, if r is greater than 1, then it means that I have also the other fixed point, that 0, x star equals 0 becomes unstable because the derivative is that. So as soon as I have a little bit of population, this will evolve and will do its course, will not go towards stability in 0. But for the other fixed points, 1 minus 1 over r, if r is greater than 0, this is f prime of x star will be less than 1 for r less than 3, and will be greater than 1 for r greater than 3. So you see that I explained the behavior that I had before. For very small r, between 1 and for small r lesser than 1, I have the exponential decay. For r between 1 and 2, I have a stable fixed point that will be reached asymptotically, and I will obtain the logistic function. Somebody has the way back right now, but I'm concluding just right now and just in time, and then I will be open for question. I'm sorry if I'm sliding a little bit late, but I think it's okay. So if r is greater than 1 but less than 2, it means that the derivative will be between 0 and 1. So will be positive and lesser, the absolute value of the derivative will be less than 1. And that means that the position will be reached asymptotically, monotonically, and you will obtain the logistic function, the one that we've seen above, like this. But if r is between 2 and 3, I will have that the absolute value of the derivative is still lesser than 1, so it's still a stable point, but the value is greater than 0, is smaller than 0. So it will alternate up and down, and will go kind of oscillating around the asymptotics. On the other hand, if r is greater than 3, in this case, the absolute value of f prime of the derivative will be greater than 1. So the fixed point, if I have any, will be unstable, and I will have a much more complicated behavior that we will see next time. Okay, I finished just on the bell. So I'm still open for question, but I think if you have other things to do, of course, you're free to go. Thank you very much for attending. Yeah, Yoar made the right question. Is value of f prime or absolute value. In this case, it was absolute value of f prime. Any
will
other question?
Will you upload the notes here?
I will share the notes. Yeah, I think I will upload them, or I will find a way to upload them. Yeah.
Okay, thanks.
I think is, yeah, I used OneNote because then I can export it and it's kind of nice. Okay. Very good. Jonas suggests to watch, I think is the Veritasium video on this logistic function where he uses computational model. So yeah, now that you've seen, and if you understand the analytics, you have to break your head a little bit, not be too relaxed to say, yeah, the computer says that it goes, then it's all fine. You should, before trying with the computer, you should understand it a little, at least a little bit, at least the main point that I stressed today. And if you understand it, and if you go through the notes and you understand that you can explain it to yourself, basically, then you can have fun and really go to Veritasium video, download the source code yourself, and play with it and see chaos in action. Are there questions or suggestions? I will stop. I will stop the recording. I hope I was recording. Yeah, I think I stopped the recording, maybe. But okay, do you have other questions? Stop share. I want to see your faces. Where are you? Okay. No questions. I see you are discussing with these friends. Still says recording. Yeah, I didn't.